National Research Council in 2012 delivered this address. It was a framework for K-12 science education practices, cross-cutting concepts and core ideas. And it was a book published by the National Academies Press. In this book, they talk about the need for science education. They looked at a whole bunch of studies, did some studies of their own, looking at lots of data to figure out what was occurring in science. Now, the background, the reason for the need for this study that they talked about was that in the mid-1980s, there was a large push for an increase in STEM education, which really that push kind of originated in the late 60s, 70s with the moon landings and the space race that was happening there, right? The United States realized that it needed to be able to be an innovator and a leader in the global economy, and the only way to do that was through STEM, which STEM, if you didn't know, stands for science, technology, engineering, and mathematics. So in their study, they looked at science as of, like this was written in 2012, what science was like then, which I believe applies to now. They looked at and saw that science was a very fact, repetitious, fill-in-the-blank subject, when they felt, and I agree, that science needs to be experienced in a deeper way. And that is really difficult because we have too many things we need to teach in our standards. I teach in the state of Utah, and if you look at the 8th grade standards, which I've taught, there is enough standards, and if I'm on an AB schedule, which I am, I have 2 to 3 days to teach each standard. Okay, and that sounds like quite a bit, but when you get into it, we'll talk about why it's not. Because this, and I'll tell you why, doesn't allow students to learn what science is and how to do it very well, because science is better learned when students apply knowledge. When you're in the real world, I'm going to put that in finger quotes that you can't see, doing science, as scientists in any field, they spend a lot of time making models, right? How does this function? If you have a water cycle model, the model is that diagram that students memorize, right? Which is not a great way to do it, but that's what we do, right? The precipitation comes down. Why does it come down? What makes it come down? There's a lot of depth there that we don't be able to get into. Coming up solutions for problems. Any problem at all has to have a solution if you want to innovate, right? And there's always new solutions you can have. And then arguing based on evidence. And I don't mean arguing on like Facebook or on the internet, just saying you're wrong. But arguing in this context is being able to state your opinion and the evidence why. One of the things that I've always agreed with and try to push in my classroom is when students disagree with me, which I'm fine with, especially with hot topic things like stem cell research or climate change or any other hot topic items. If you have reasons, right, evidence, data, right, thought out logical reasons, then I'm okay with that. You need to have a reason, right? If it's just, well, my dad doesn't believe in climate change, so I don't, that's not a reason. You have to go figure out why you think what you think and see if that agrees with it, right? Right. And this also enables students to see the nuance in the scientific method. And I can't speak for all experiences, but when I've seen the scientific method taught, when I've taught it sometimes, and when I was taught it over 14 years ago when I was in school, there was a big, you have to do it in a certain order, right? You have to come up with a question. Then you got to come up with your hypothesis. Then after you have your hypothesis, you figure out how you're going to test your hypothesis. And then as you test it, you gather data and you get your results. And then you come back to your conclusion. Was your hypothesis right or wrong? When, yes, that is a good way to do it. And that is how science is done, right? Those steps occur in traditional science. In applied science, it's much more nuanced. So if you were, let's say you were on a project after a fire and you had an idea that I need to do this a certain way. I need to first put down grass seeds and then trees, and then I got to do forms, right? But then you later learn with reasons why that doesn't work, and you put down the graphs. You're not going to continue if it's not going to work, right? If new knowledge comes forward, you need to be able to react, and that's where this comes back. This is a fluctuating thing. It's not a step-by-step. Since my hypothesis is this, I have to stick with it all the way to the end, right? If things change, if your idea changes, that's okay. What else did they talk about that's missing? Not only is there too many things to talk about in science, right, but there's also, we don't spend enough time on it. So with these tens of thousands of teachers that they gathered data in a survey from, elementary teachers self-disclosed that when they teach science, which is not on here, but usually is only like twice a week out of 5 days, they teach for about 20 minutes. And I put the about here because they break it up into 3 age groups in elementary school, but they're all within 4 minutes of 20. K through 2, I believe, was 18. Then 3 and 4 were 22, and then 25 minutes was for 5th and 6th. Right, and then math receives about 60 minutes, same thing, right around there, within a few minutes, and language arts is around 80 minutes. That's 56 in the frameworks that I had at the beginning, right? So when it is taught, they also noticed not enough time, one thing, but also because it's so short, it's very factual, fill in the blank. Like, what are the 3 types of clouds? Oh, boom, boom, boom. Not the 3 types of clouds. Why do they matter? What do they do? Why do we care? When you look in the sky and you see this cloud, what do you think might occur? Different things. What causes them to occur the way they are? Why, when you live here, you're going to see this type of cloud more than, right? So there's deeper things there and reasons why we care about cloud type than just here, memorize these 3. And also, over half the teachers at all the levels do not have students use evidence more than once a week. So they did not only elementary, but middle school and high school, and it was right around 45 to 51% only have their students use evidence once a week. So about half not even do it once a week. The percentage that used it every day was extremely small, averaging from like 5 to 11%. When evidence, as I mentioned, is key to understand the reasons, right? Evidence is the reasons why we think these things. Why did Einstein have his theories, which is a high school thing, right, about E equals mc squared? The reason's there. It's not, let's just trust Einstein and roll with it. That's not what happened. And that's not what should be learned, right? And teachers that do labs, which is great, right? This always have hands-on, it's a big part, but they're usually like a cookbook. Here's step 1, here's step 2, which I've even fallen into that trap many times because it is tough, time-wise, and to write a lesson that lets students explore. Right? How do we keep students engaged? How do we help them learn and give that control away and let them explore? A topic is very difficult, right? Because if I'm using a water plant and put in water and I want them to learn that more sunlight equals more photosynthesis, right? Plants turning sunlight into energy, then I want them to do it a certain way so they see that outcome, which is not always a great way to teach a lab. Right? And not only do teachers not have time, or they might be, not teaching it the best way due to how they were taught when they were in their programs, if they were in their programs, right? As we learned, many are not even in the correct program, but teachers, this is if they feel like their class is adequate, right? This is the teachers telling us what they feel. So 31% here at the beginning of elementary teachers believe that their facilities are adequate. 69% do know what that means, right? So they don't have any lab tables, or they don't have electrical outlets, faucets, or sinks, right? 57% of middle school feel that way. For instance, in my school, there is 3 of us 8th grade science teachers. 2 of us have a sink, 1 of us does not. We would fit into that category very easily. And I know it's about the same percentage with the 7th grade science teachers, right? And if that changes and gets better as you go into high school, as they get more specialized. Okay, equipment, there's the numbers right? Not very great. Consumable materials, 34% of elementary, right, up to 59 in high school. So still not great consumables to do labs, which is a huge part of doing labs as things get used up, right? And then having instructional technology, having students use calculators or computers, which probes and sensors. I have never experienced or seen using probes and sensors in a science classroom, in my experience now. Obviously some do, but I would be part of the other side of this 37%. Okay? So teachers don't even have the adequate resources to teach science in a way, this is from page 58, that would allow them to teach these deeper ways, to have students problem solve, to open explore. Okay? Like I mentioned, teachers are teaching outside of their expertise, and it's not their fault, right? They need a job, they apply for jobs, or they're teaching somewhere and their principal says, hey, we need to you to teach this as well, and you do because, right? So your principal, you kind of need to do what he's having you do, or you're scared of consequences, right? And in grades 6 through 8, middle school, any certification at all in science, only up to 60% of teachers have any certification to be teaching the science they're teaching. High school, that jumps up dramatically, right? And then in the subject they teach, if you teach general science like we do in Utah for middle school, only 42% of the teachers hold a teaching certificate for that. Biology, which my degree is in, which I also have certifications for general science. That's why I would fit into the other side of that category. That there is only up to less than half have degrees in that, and you can go through that, right? Physics, though, dramatic. In middle school, if physics is being taught, only 9.2% of those teachers have physics certifications, right? When in high school, it's still the lowest. Only 60% have it in high school. So as you can see, there's a large issue. There's a large gap here with what teachers can do based on what their certifications are, which is, once again, they get the certifications what they can and take whatever jobs they can. So that's not really on them. That's a systemic problem, right? The amount of materials they have, which is due to budgets or ways of procuring them, because teachers, time-wise, it is difficult, as I will attest to, find all the different materials, even if you do come up with a cool lab. Where do I order a high percentage of hydrogen peroxide? Because the stuff at the store is only this percent, but it says I need that percent. Where do I go to do that? Right? Figuring out all those questions takes time. And not only that, but there's not enough of that time, if you were to do that, to teach everything that you're required to teach by law, which is the standards of your state, right? To teach them deep enough to help students understand. So here's some issues in science education as of, I believe, still today, as they talked about here from 2012.